What if the end of a story was also its beginning? What if the cosmos, in its infinite and terrifying wisdom, operated not just on a forward-moving arrow of time, but on a loop, a Mobius strip of creation and dissolution, where death and birth were two sides of the same incomprehensible event? For generations, we have looked out into the darkness and seen the universe's great endings. We have witnessed the death throes of colossal stars, their final magnificent detonations painting the void with the elements of life. We have charted the locations of black holes, those gravitational tyrants that represent the ultimate cosmic dead end, a place where light space and time itself surrender. Our story of the universe has always been one of glorious decay, of a slow, inexorable march from a fiery beginning toward a cold, silent end. But on a Tuesday in late autumn, while Earth slept, and our silent sentinels in orbit kept their unblinking watch, that story was ripped apart. For 3.7 seconds in a patch of sky so empty, it was remarkable only for its profound blackness. Something impossible happened. It wasn't an explosion in the way we understand them. It was more like a wound opening in the fabric of reality itself. A silent, instantaneous scream of light and energy erupted from nothing. There was no prelude, no rising crescendo of a dying star, no gravitational shriek of colliding titans. One moment there was the void, cold and absolute. The next, a fountain of gamma rays, X-rays and exotic particles of such purity and intensity that it momentarily blinded the most sophisticated instruments humanity has ever placed in space. The data cascaded down to Earth flooding servers at Goddard, at the European Southern Observatory, at control centres across the globe. Initially it was dismissed as an instrumental glitch, a cosmic ray striking a sensor just so creating a phantom signal. Such things happen. The universe is a noisy place, and our telescopes are sensitive enough to hear its faintest whispers and occasional static. But this was no whisper. This was a coherent, structured and terrifyingly powerful shout from the depths of intergalactic space. As automated systems cross-referenced the event, a chilling consensus emerged. The James Webb, Hubble Chandra and Swift telescopes, all separated by millions of miles, had all seen the exact same thing at the exact same instant. It was real. It was out there, and it made absolutely no sense. The first assumption, the logical and rational one, was that we had witnessed a hypernova, the cataclysmic collapse of a star more than 100 times the mass of our Sun, giving birth to a black hole in a flash of gamma rays. This is the universe's most violent known event, a celestial blowtorch that can outshine its entire host galaxy for a few brief, terrible seconds. The teams on the ground, now buzzing with a mixture of excitement and trepidation, began the standard protocol. They searched for the afterglow. A gamma ray burst, for all its ferocity, is messy. It punches through the interstellar medium superheating gas and dust, leaving behind a fading multi-wavelength ember that can be studied for days, weeks, even months. It is the cosmic fingerprint of the murder weapon. But when they looked, there was nothing. Absolutely nothing. The phantom light had vanished without a trace, leaving behind only the cold, unperturbed vacuum that was there before. The spectrum of the burst was also wrong. It was too clean, too perfect. A stellar explosion is a chaotic soup of elements, each leaving its signature in the light, a barcode telling us of its life and violent death. This burst had no such barcode. It was a pure, featureless continuum of energy, as if it had been generated not from the messy physics of matter, but from the pristine mathematics of space-time itself. The first and most powerful explanation in our astrophysical toolkit had been rendered useless. Perhaps then it was a magniata, a neutron star with a magnetic field of such nightmarish intensity it could rip you apart atom by atom from 100,000 miles away. These cosmic dynamos are known to produce sporadic, ultra-powerful flares. The teams pivoted, searching for the telltale pulse of a rapidly spinning stellar remnant, the gravitational anchor that should lie at the heart of such an outburst. Again, they found only emptiness. Moreover, the burst's location was deeply problematic. It originated in the profound, lonely darkness between galaxies, a place known as the Void. While not entirely empty, it is a region where star formation is exceptionally rare. To find a magnetar, there would be like finding a blue whale in the middle of the Sahara Desert. It was statistically profoundly, almost cosmologically impossible. The second pillar of high-energy astrophysics had crumbled. The mystery deepened and a quiet anxiety began to creep into the analysis rooms. The universe was not playing by its own rules. What else could it be? A tidal disruption event where a star wanders too close to a supermassive black hole and is shredded by its gravity? No. Those events are long drawn-out affairs unfolding over months as the star is unspooled like a thread of luminous pasta. This event was over in the time it takes to draw a breath. A kilonova, the collision of two neutron stars. A spectacular possibility, one that forges heavy elements like gold and platinum in a radioactive furnace. But such a collision would have drenched the cosmos in gravitational waves, a ripple in space-time that our LIGO and Virgo detectors would have picked up as a clear ringing chime. They heard only silence. Every single known phenomenon, every catastrophic event that we have spent a century observing and cataloguing was systematically and definitively ruled out. Scientists, people who dedicate their lives to finding patterns and explanations, were left holding a piece of a puzzle that did not fit into our picture of the universe. It was a single 3.7-second data point that threatened to invalidate entire libraries of knowledge. It was an anomaly so profound it bordered on the philosophical. It came from nowhere. It was made of nothing we could recognize, and it vanished, leaving behind not an echo, but a question mark hanging in the infinite dark. That question mark forced a few brave and perhaps reckless minds to dust off a ghost that has haunted the pages of physics for 100 years. A concept so strange, so counterintuitive, that most have relegated it to the realm of mathematical fantasy. It is an idea born not from observation, but from the elegant and demanding symmetry of Einstein's equations of general relativity. When Einstein formulated his theory, he described how mass and energy warp spacetime, creating what we call gravity. The most extreme solution to these equations gave us the black hole, a region of spacetime so warped that nothing, not even light, can escape. It is a one-way door to infinity, the universe's ultimate prison. But the mathematics, in its cold and impartial logic, allowed for another solution, a perfect time-reversed mirror of the first. If you can have a region where nothing can get out, symmetry demands a region where nothing can get in. A place where space-time is warped not into an inescapable pit, but into an explosive, impassable fountain. A cosmic geyser erupting from a singularity. They called it a white hole. For decades, this was little more than a curiosity, a playful what-if for theorists. No one knew how a white hole could possibly form in our universe. A black hole is the natural endpoint of gravitational collapse. A massive star dies, its core implodes, and a black hole is born. But a white hole, for it to exist, it would have to have been there since the very beginning of time itself, a primordial anomaly woven into the initial fabric of the Big Bang. It is an object that can only ever decrease in mass, a spontaneous and violent outpouring of matter and energy from a point of infinite density. It is by its very definition an unstable, ephemeral and singular event. A white hole cannot be fed, it cannot be sustained. It can only erupt once in a blinding flash of pure creation, and then fade from existence, its purpose served. It is the ultimate cosmic source, a beginning with no discernible past. It is the physical manifestation of the phrase, "Let there be light." And as physicists looked at the impossible data from this burst, its appearance from nothing, its pure energy signature, its lack of an ancestor or an afterglow, the outlandish heretical thought began to take hold. Could this be it? Could we have accidentally stumbled upon the first ever direct observation of Einstein's forgotten child? To even propose such a thing is to stand on the very edge of known science. It feels less like astronomy and more like mythology. White holes break our most cherished rules, most notably the second law of thermodynamics, which states that entropy or disorder must always increase in a closed system. A black hole is a perfect embodiment of this law, taking ordered matter and crushing it into a disordered, chaotic singularity. But a white hole does the opposite. It spontaneously spews out highly structured matter and energy from that same singularity, seemingly creating order from chaos, reversing the irreversible flow of cosmic time. It suggests that information isn't lost forever in a black hole, but perhaps it is recycled. It hints that the universe might have not just cosmic sinks, but cosmic fountains. That for every gravitational graveyard there might be a corresponding celestial nursery. The implications are staggering, forcing us to reconsider the life cycle of the universe itself. Is it possible that what falls into a black hole in one epoch or even in one parallel universe could re-emerge from a white hole in another? Is this burst we witnessed not just an explosion, but a message, a delivery, the birth of a new patch of space-time seeded with matter from a long-dead past? The data is uncompromising. The theories we have are insufficient. We stand at a precipice staring into a chasm of ignorance, armed with a single tantalizing clue. This 3.7-second flare from the void could be a fluke, a new and bizarre type of stellar death we have yet to categorize a phenomenon that will eventually be explained by conventional physics. Or it could be the key. The first crack in a dam of understanding, a glimpse into a new reality that operates on principles we're only just beginning to imagine. It forces upon us the most profound question we have ever had to ask of the night sky. Are we witnessing for the first time not the end of a star but the beginning of a universe? Are we seeing the echo of a black hole's last meal spat back out into existence? To even begin to answer that, we have to journey back through the life and death of stars, deep into the warped and twisted heart of a black hole itself, and then further still to the one event that might hold the secret to both. The moment of creation, the Big Bang. Because somewhere in the physics of our own origin lies the truth about this impossible light, and the ghost it may have unleashed upon our cosmos. What if the most fundamental law of the cosmos was not a law at all, but a fragile suggestion? For over a century we have built our entire understanding of the universe upon a set of rules we believed were carved into the very fabric of space-time. These are rules of gravity and destiny rules that tell us what goes in cannot come out. They are the ironclad principles that govern the life cycle of stars and the architecture of galaxies, dictating an arrow of time that moves in only one direction. We have trusted these rules. We have built our models upon them, launched our probes according to their predictions, and mapped the heavens with their elegant mathematics as our guide. This cosmic constitution, written in the language of Einstein's relativity, has served us faithfully, revealing a universe that is both terrifying and beautiful. But it also contains a whisper, a footnote of impossibility that we have long chosen to ignore, a hint that for every rule there might be an exception, a secret that suggests the universe might have a back door. And if that's true, then everything we think we know about finality, about endings, is about to be challenged by a single inexplicable burst of light from the void. To understand the revolution that may be unfolding in the deepest dark, you must first understand the established order, the undisputed tyrant of cosmic law, the black hole. We speak their name with a familiar sense of dread and wonder, these celestial behemoths that have captured our imagination for decades. They are not science fiction. They are as real as the ground beneath your feet, and their existence represents the most extreme victory of gravity over all other forces in nature. The story of a black hole is a story of collapse of an ending so absolute that it tears a hole in reality itself. It begins with a star, a massive, brilliant giant, many times heavier than our own sun, living a life of furious thermonuclear creation. For millions of years it forges new elements in its core, its internal furnace pushing outward with unimaginable force, perfectly balancing the relentless inward crush of its own gravity. It is a titanic struggle, a gravitational stalemate that defines the star's entire existence. But this cosmic balancing act cannot last forever. Eventually the star's fuel runs out, the furnace cools, the outward pressure fails, and gravity, the patient, persistent force that has been waiting since the star's birth, finally claims its prize. In less than a second, the star's core collapses under its own colossal weight. The outer layers rebound in a cataclysmic explosion we call a supernova, a detonation so bright it can outshine its entire home galaxy for weeks. It is one of the most spectacular displays of cosmic power, a final brilliant gasp before the end. But what is left behind in the quiet aftermath of this violence is something far more profound. If the remnant core is massive enough, gravity's victory is total. It crushes matter past every known physical limit, squeezing it beyond the point of atoms, beyond neutrons, into a state of infinite density our physics cannot yet describe. It becomes a singularity, a point where space and time themselves curve into an endless bottomless pit. This is the heart of a black hole, but it is a heart we can never see. Surrounding this point of impossible physics is a boundary, a perfect spherical membrane of darkness known as the event horizon. This is not a physical surface you could touch. It is far more fundamental. The event horizon is the precise point in space where the gravitational pull becomes so immense that the escape velocity exceeds the speed of light. It is a one-way door to eternity. Anything that crosses this threshold, a stray asteroid, a wandering planet, a doomed star, even a beam of light, the fastest thing in the universe, is irrevocably captured. It cannot turn back. It cannot send out a signal. Its fate is sealed. It will be pulled inward, stretched and torn apart by tidal forces, and ultimately crushed into the singularity its mass added to the black hole's own. From our perspective outside this celestial prison, the object would appear to slow down its light redshifting into oblivion as it approaches the horizon, frozen in time for an eternity at the edge of forever. For many years, this breathtaking concept remained a prediction, a monstrous ghost lurking in the mathematics of Einstein's equations. We saw the shadows they cast, the chaos they created in their cosmic neighborhoods, but we had never truly seen one. That has all changed. We have now moved beyond inference and into the realm of direct observation, transforming black holes from theoretical curiosities into tangible astronomical objects. We have watched stars orbiting nothing. In the heart of our own Milky Way, astronomers have meticulously tracked the frantic dance of massive suns whipping through space at millions of miles per hour. They are all pirouetting around a single unseen point of immense gravitational power, a dark anchor holding our entire galaxy in its grip. That anchor, Sagittarius A, is a supermassive black hole 4 million times the mass of our Sun. We cannot see it, but we can see its absolute authority over everything around it. We have seen the feasts of these invisible giants. When gas and dust from a nearby star stray too close, they are ensnared in a gravitational whirlpool, forming a swirling, superheated structure called an accretion disk. As this material spirals toward the event horizon, friction and magnetic forces heat it to billions of degrees, causing it to glow with an intensity that can be seen across the cosmos. This is the black hole's calling card, a blazing testament to its destructive power. These accretion disks and the powerful jets of energy they sometimes launch from their poles are some of the brightest objects in the universe. We see them, we map them, we analyze their light, and in doing so we trace the outline of the monster that lurks at their center. And most profoundly of all, through a global network of radio telescopes working in concert, we have finally captured its silhouette. The Event Horizon Telescope gave humanity its first direct image of a black hole's shadow, the dark abyss of M87, its event horizon starkly outlined by the fiery ring of captured light. It was a triumphant confirmation of a century of theory staring back at us from 55 million light-years away. The case, it seemed, was closed. Black holes are the universe's ultimate endpoints, the final resting place for matter and energy. They are the great cosmic sinks where information is lost, and from which nothing, not even light, can ever escape. This is the law. And yet the very same equations that so perfectly predicted these cosmic prisons hold a secret, a dark mirror to the reality we have come to accept. When physicists explored the full mathematical landscape of Einstein's general relativity, they found a second equally valid solution, a strange and unsettling twin to the black hole. This solution describes an object that is its exact opposite in every conceivable way. It is not a sink but a fountain. It is not an end but a beginning. It is an object from which matter and energy erupt but into which nothing can ever enter. They called it a white hole. On paper, it is the perfect time reversal of a black hole. Imagine taking a film of a star collapsing into a singularity and playing it backward. You would see an infinitely dense point spontaneously erupt, spewing out matter and energy, creating a star and expanding outward. That explosive generative event is a white hole. Like its dark sibling, a white hole possesses a singularity and an event horizon, but its properties are inverted, turned inside out in a way that seems to defy all logic and experience. The singularity of a white hole lies not in the future, as it does for anything falling into a black hole, but in the past. It is an origin point, a moment of creation that has already happened. The event horizon of a white hole is not a barrier you cannot escape from, but a barrier you cannot get into. If you were to travel in a spaceship toward a white hole, you would find yourself fighting a current of spacetime that was flowing unstoppably outward. You could fire your engines at full power, you could even travel at the speed of light, but you would never be able to cross its boundary. You would be forever repelled, pushed away by a force that wasn't a force at all, but the very shape of reality itself. From this enigmatic object, light and matter would pour forth continuously, like a cosmic spring with an inexhaustible source. It's a beautiful, poetic, and utterly bizarre concept, a place where the universe is born anew, a cosmic font of creation to balance the cosmic graveyards of black holes. But for all its mathematical elegance, the white hole has been relegated to the dusty attic of theoretical physics for one very simple, very powerful reason: we have never seen one. Not a hint, not a whisper, not a single shred of evidence from the entire observable universe suggests that they exist. They seem to be purely mathematical ghosts, artifacts of a theory that allows for possibilities the universe has chosen not to embrace. There are profound physical reasons for this dismissal. The formation of a white hole is a paradox. For a black hole to form matter must collapse an event we see happen all the time with dying stars. For a white hole to exist, it would seemingly have to have been there since the beginning of time itself, a primordial object born in the Big Bang, since no known physical process could create one in the current universe. Furthermore, white holes appear to be aggressive violators of one of the most sacred laws of physics, the second law of thermodynamics. This law dictates that entropy or disorder in a closed system must always increase over time. Things fall apart, stars burn out, energy spreads and dissipates. It is the law that gives time its arrow pointing from the ordered past to the chaotic future. Black holes are champions of this law. They take in ordered matter like stars and planets and convert it into the ultimate state of disordered information hidden behind an event horizon. But a white hole does the opposite. It would be a source of spontaneous, uncaused creation, a machine for decreasing entropy. It would take the chaos of a singularity and erupt with structured matter and energy, effectively reversing the flow of time's arrow in its vicinity. It would be a profoundly unnatural object, an affront to the cosmic order we have so carefully observed. Physicists have also shown that even if a white hole could somehow form, it would be catastrophically unstable. The slightest perturbation, even a single stray photon, attempting to cross its event horizon from the outside, would theoretically cause it to collapse instantly into a black hole. In a universe filled with cosmic microwave background radiation, stray particles, and light from distant galaxies, a pristine, untouched white hole simply could not survive. It's like trying to protect a soap bubble in the middle of a hurricane. Its existence is a theoretical knife edge too fragile to be real, and so we, as astronomers and scientists, have built our models accordingly. We have designed our instruments and our search strategies based on this fundamental asymmetry. We scan the heavens for the telltale signs of consumption, not creation. We look for the shadows, the accretion disks, the gravitational lensing that signal matter going in. We expect to find the darkness of gravitational prisons, the silent one-way gates of black holes. We do not expect to find fountains of light erupting from nowhere. We do not expect to see the universe playing its movie in reverse. The cosmic stage as we understood it was set. On one side, the well-documented, observationally confirmed reality of black holes, the universe's predictable, all-consuming engines of finality. On the other, the ghostly, mathematically permitted but physically forbidden fantasy of white holes, a concept relegated to thought experiments and blackboard debates. The rules were clear. The categories were distinct. Our telescope's sophisticated instruments designed to confirm this very picture of the cosmos swept the sky year after year, reinforcing this worldview with mountains of data. They saw stars die. They saw black holes feast. They saw the universe behaving exactly as it should. Until they saw something else. Something that didn't fit. A signal from the depths of intergalactic space that conformed to no known category of cosmic event. A sudden impossible burst of energy from a patch of sky that was supposed to be empty, a location of absolute featureless dark. It was a flash of light from a place of perpetual night, a scream of creation from a void that should only ever consume. The first anomaly had arrived, and with it a terrifying question began to form: what if the ghost in the machine is real? And so we had spent a century staring into the abyss, cataloguing the endless ways the universe could die. We had built our theories on the beautiful, terrible logic of endings on matter crushed and light devoured. But we had never, not once, seriously prepared ourselves for the opposite. We had never looked for a beginning emerging from nowhere. The first hint arrived not as a trumpet blast, but as a sterile, automated whisper in the digital dark. It was a burst of anonymous data, a fleeting packet of information fired from the Swift Observatory, a vigilant hunter circling silently 500 kilometers above our heads, its primary mission to catch the fleeting death cries of stars. On this day, it caught something else entirely. The alert designated GRB 26334. Theme A was initially unassuming, just another potential gamma ray burst in a lonely, unremarkable patch of sky in the constellation of Coma Berenices. Across the globe in control rooms from Goddard to Leicester, the message rippled through the system. Telescopes, robotic and unthinking, received their new orders, slewing their great mirrors and dishes toward the designated coordinates, an act repeated a dozen times a week. For the first few minutes it was business as usual, a choreography of automated precision. But then the humans began to look. The first astronomers to see the raw data felt not a jolt of discovery, but a prickle of confusion, a sense of deep cognitive dissonance. The light curve, the simple plot of brightness over time was wrong. It was impossibly fundamentally wrong. Gamma-ray bursts, the universe's most violent explosions, are the savage signatures of a star's final catastrophic collapse, or the collision of two neutron stars. They are messy, complex, and follow certain brutal rules. They rise in a chaotic flurry of photons, a jagged crescendo of gamma-ray violence, and then they fade over minutes or hours, leaving behind a smouldering afterglow. This was different. This was clean. The data showed an ascent of pure, coherent energy rising to a brilliant peak in less than 10 seconds, a perfectly smooth, almost mathematically pure ramp-up. And then, just as bizarrely, it simply stopped. There was no lingering decay, no fading ember. The light curve was a perfect symmetrical mountain. It was as if someone had flipped a cosmic switch on, and then just as cleanly flipped it off. The universe doesn't work that way. Nature is violent and chaotic, not sterile and precise. It was the first sign that our catalogue of cosmic deaths was missing a chapter. The global astronomical community, connected by the instant sinews of the internet, began to pivot a great thinking machine, focusing its myriad eyes on this one bewildering spot. The initial suspect, as the automated alert suggested, was a gamma-ray burst to GRB. They are the titans of cosmic explosions, the brightest event since the Big Bang itself. For a few terrifying seconds, a GRB can outshine all the stars in the observable universe combined, a celestial blowtorch visible from billions of light-years away. They come in two main flavours: short bursts lasting less than 2 seconds, believed to be the death dance of merging neutron stars, and long bursts, the death throes of colossal spinning stars, their cores imploding into black holes, while their outer layers are blasted into space by jets of unimaginable power. Our strange signal, lasting about 10 seconds, fell awkwardly between these two established families. It was too long to be a classic short burst, yet the energy profile was all wrong for a long one. Long bursts are powered by the messy collapse of a giant star, a process that leaves behind a very specific fingerprint. The gamma rays they emit are a chaotic mix of energies, a spectrum full of lumps and bumps as the radiation fights its way out of the star's dense collapsing shell. This new event was spectrally pure. The gamma rays were almost thermal, as if they had been emitted from a single unified surface, expanding at nearly the speed of a light. It was a clean burn, not the shrapnel-filled chaos of a stellar collapse. The most damning evidence, however, came from what was missing. A GRB, no matter its origin, is the trigger for a far larger event. Its jets punching through space slam into the surrounding gas and dust, creating a spectacular fading afterglow that can be seen for weeks or even months in X-rays, visible light, and crucially radio waves. It's the cosmic equivalent of a bullet sonic boom. The burst is the flash, the afterglow is the thunder. So we listened. The Very Large Array in New Mexico, the Atacama Large Millimeter Array in Chile, a global network of immense sensitive ears all turned toward that silent patch of sky, straining to hear the faint radio echo of that impossible blast. They heard nothing. Day after day, the observations returned only the cold, empty hiss of the cosmic background. There was no afterglow, no X-ray ember, no optical glimmer, no radio whisper. It was a flash without a bang, a gunshot without a sound. This single glaring absence was a profound violation of physics. It was like seeing a lightning strike that left no thunder in its wake. The first and most obvious suspect, the gamma-ray burst, had an ironclad alibi. It simply could not have been the culprit. A sense of unease began to creep through the community. If it wasn't the most powerful explosion we know of, what was it? The next logical candidate was the supernova. Perhaps this wasn't the birth of a black hole, but the spectacular death of a more conventional star. A supernova is one of nature's grandest acts of recycling. A star many times the mass of our sun exhausts its fuel, its core collapsing under its own immense gravity before rebounding in a titanic explosion that seeds the cosmos with heavy elements, the very iron in your blood, the calcium in your bones. These explosions are stupendously bright, but they are also slow. They take days or even weeks to reach their peak brightness, and then they fade majestically over many months. Their light is powered by the radioactive decay of newly forged elements, primarily an unstable isotope called nickel-56, which decays into cobalt-56 and then into stable iron-56. This slow, predictable radioactive clock is the supernova's heartbeat, imprinting a distinctive, slowly dimming curve onto its light. Our event had peaked and vanished in under a minute. Its timeline was fundamentally incompatible with the slow-burn physics of radioactive decay. It was like comparing the flicker of a firefly to the slow, steady burn of a forest fire. But astronomers are nothing if not thorough. The great optical telescopes Keck Gemini, the Hubble Space Telescope itself, stared deeply into the location of the burst, searching for the telltale signs of an exploding star. They were looking for a ghostly expanding cloud of stellar guts, a nebula of superheated gas rushing outwards at thousands of kilometers per second. They found nothing, just the placid, undisturbed vacuum of intergalactic space. Even more, they used their powerful spectrographs to sift through the faint light from that region, hunting for the specific spectral lines of nickel, cobalt, and iron, the smoking gun of a supernova. The spectrum was utterly clean. It held no trace of the heavy elements that must by definition be present after such an explosion. It was a death without a body, a cosmic crime scene wiped clean of all forensic evidence. The supernova hypothesis, elegant and familiar, was dead. The checklist of known cosmic cataclysms was growing shorter, and the sense of strangeness was growing deeper. What was left? Perhaps the violence wasn't stellar but gravitational. The attention turned to two of the most exotic and terrifying objects in the universe, magnetars and black holes. First, the magnetar. Imagine a star more massive than the Sun, crushed by its own gravity, into a sphere just 20 kilometers across. An object so dense a single teaspoon of it would outweigh Mount Everest. This is a neutron star. Now amplify its magnetic field to 1,000 trillion times that of Earth's. A field so powerful it could wipe a credit card from the distance of the moon, so intense it would warp the atoms in your own body. This is a magnetar. They are the most powerful magnets in the cosmos, and they are unstable. Sometimes their colossal magnetic fields rearrange themselves in a violent starquake, snapping and reconnecting with unimaginable force. This releases a colossal flare of high-energy radiation, a blast of gamma rays that can for a fraction of a second be catastrophically powerful. In 2004, one such flare from a magnetar in our own galaxy was so intense it physically compressed the Earth's ionosphere. Could our mystery signal have been a giant flare from a distant magnetar? The idea was tantalizing. A magnetar flare is a purely magnetic event, not a messy stellar explosion, which could explain the lack of debris and the strangely clean energy signature. It fit some of the evidence, but it failed catastrophically on two key points: location and energy. Magnetars are the children of massive stars, and like those stars, they live and die in the bustling, star-filled spiral arms of galaxies. They are city dwellers found where the action is. But when astronomers pinpointed the location of our burst, they found it in the loneliest place imaginable. It wasn't in a galaxy at all. It was in the vast empty chasm of intergalactic space, a void between two ancient elliptical galaxies, a place where massive stars haven't been born for billions of years. It was a cosmic ghost town, the last place you would ever expect to find a young volatile object like a magnetar. It was like finding a newborn baby in the middle of the Antarctic. And then there was the sheer power of the event. Even the most titanic magnetar flare we've ever conceived of pales in comparison to the energy unleashed by this burst. To generate this much light, a magnetar would have had to effectively annihilate itself, converting a significant fraction of its own mass directly into energy. It was an energy budget that broke the models. The physics simply didn't hold up. The magnetar, a monster of cosmic proportions, was still not monster enough. The suspect was crossed off the list. This left one final plausible mainstream suspect. A process so quintessentially Einsteinian in its horror and grandeur that it has become a staple of cosmic imagination, the tidal disruption event, or TDE. This is what happens when a wandering star makes its final fatal mistake. It strays too close to a supermassive black hole. The black hole's gravity is not uniform. The side of the star closer to the black hole is pulled with incomprehensibly more force than the far side. This differential gravity, the tide, stretches the star. First, it is pulled into the shape of an egg, then a cigar, and then in a process horrifically nicknamed spaghettification, it is drawn out into a single, luminous streamer of stellar plasma thousands of kilometers long. As this streamer of star stuff whips around the black hole, it is accelerated to near light-speed heats, up to millions of degrees, and unleashes a brilliant lingering flare of X-rays and ultraviolet light. A TDE is the signature of a black hole feeding the last scream of a star being devoured whole. Here finally was a suspect that seemed to fit the bizarre location. Supermassive black holes lurk at the hearts of most large galaxies, including the ancient elliptical galaxies that flanked the location of the burst. Perhaps a star had been gravitationally slingshotted out of its home galaxy, only to meet its doom by a lonely quiescent black hole drifting through the intergalactic void. It was a plausible if dramatic scenario. The search began for the central engine of the crime. Using the deepest images from Hubble and the Chandra X-ray Observatory team scoured the region for the faint gravitational or radiological signature of a massive black hole. They found nothing. No subtle lensing of background starlight, no faint halo of hot gas that should surround such a behemoth. The throne room was empty, but the most damning evidence once again was the light curve. The tail of the tape. A TDE, for all its violence, is a relatively slow and a messy process. The flare brightens over weeks as the stellar material falls inward, and then it fades over months, following a very specific predictable pattern as the accretion disk is slowly consumed. The brightness fades according to a simple physical law, decaying proportionally to time to the power of -5/3. It's a calling card written into the physics of the event. Our signal had no such signature. It didn't rise over weeks, it rose in seconds. It didn't fade over months, it vanished in an instant. It was not the messy, lingering signature of a star being eaten. It was something else, something instantaneous, something reversible. The tidal disruption event, the last great hope for a conventional explanation, was ruled out. And with that, the astronomers fell silent. They had exhausted the catalogue. They had paraded every known cosmic monster across the stage: the collapsing star, the exploding star, the magnetic star, the devoured star, and not a single one fit the description of the perpetrator. Every single theory had failed, and it failed not on minor details but on the fundamental pillars of the models. The timescale was wrong, the energy was wrong, the spectrum was wrong, the location was wrong, the afterglow wasn't there at all. This is a moment that rarely happens in modern science. It is the moment where the data is undeniable, The observations are pristine, confirmed by instruments across the planet and above it, and yet it corresponds to nothing in the textbooks. It is the moment a cartographer discovers an island that simply should not exist. The frantic energy of the initial chase, the rush of ruling out suspects, gave way to a much deeper, more unsettling emotion, a profound, unnerving quiet. The feeling of standing at the edge of a vast dark ocean of ignorance. They were adrift with gigabytes of data that pointed in all its pristine and terrifying clarity to a complete and utter gap in our understanding of the universe. All of our stories about how things end, all of our models for cosmic death had been found wanting. The event was not an explosion. It was not a collision. It was not a flare. It behaved like an appearance, a spontaneous, inexplicable arrival of energy from a place where there should have been nothing. And in the quiet hum of computer servers as scientists stared at that perfect symmetrical mountain of light, a deeply unsettling and long-forgotten idea began to surface. An idea born not from observation, but from the purest, most beautiful mathematics. The idea that if you can have an object from which nothing can escape, then perhaps somewhere you must have its perfect opposite. An object from which everything must emerge. And so, the frantic worldwide conversation continued, a symphony of inquiry played out across secure servers and late-night video calls. Every new analysis of GRB 23119 seemed to peel back a layer of understanding, only to reveal a deeper, more profound abyss of ignorance beneath. The light curve, that delicate fingerprint of cosmic violence, was clean. Too clean. There was no precursor shimmer, no flicker of a dying star, none of the telltale X-ray flashes that often precede the main event. The cataclysm had simply switched on as if a god had thrown a lever in the dark. And the afterglow, the thing that should have been a simple fading ember, refused to cooperate. It was behaving like a fire that grew hotter as it ran out of fuel, a shout that became a roar the farther it travelled from its source. This was the central maddening paradox that brought the global astrophysics community to a grinding halt. In every gamma-ray burst ever recorded, from the most titanic hypernova to the collision of two neutron stars, the physics follows a simple intuitive rule. Energy cascades downwards. The initial explosion is a blitz of the highest energy photons, hard gamma rays, which then slam into the surrounding medium. This cosmic collision creates a shock wave, a torrent of radiation that cools over time. Gamma rays give way to X-rays. X-rays soften into ultraviolet and visible light. Visible light stretches into the infrared, and finally, weeks or months later, a faint whisper of radio waves is all that remains. It's a waterfall of energy, always flowing from high to low, from hot to cold, a perfect expression of entropy on a celestial scale. But GRB 231109 was not a waterfall. It was a river flowing uphill. As the afterglow evolved, the peak of its energy output didn't shift downwards toward the reds and the radios. It climbed. Subtle at first, a detail lost in the error bars of the initial data, the trend became undeniable as more observatories locked on. The X-ray signature was intensifying, its spectrum hardening, evolving into energies it should have been leaving behind. It was as if we were watching a film of an explosion, but the projector was running in reverse. The shattered pieces were flying back together, reassembling themselves into a single brilliant point of impossible heat and light. This single fact broke every model we had. A collapsing star cannot do this. Its physics is a one-way street toward decay and diffusion. A kilonova, the golden flash of merging neutron stars, is an act of cosmic dispersal, not impossible regeneration. For weeks, the world's most brilliant minds threw every conceivable explanation at the anomaly. Perhaps it was a complex jet structure, a spiraling beam of energy whose hotter core was only now swinging into our line of sight. Plausible, but the models required a geometry so contrived, so perfectly and bizarrely aimed, that it seemed less like science and more like a desperate appeal to cosmic coincidence. Maybe it was an interaction with a dense unseen shell of dust far from the source, causing a secondary shockwave that was reheating the outflow. But the host galaxy was an ancient gossamer-thin dwarf, utterly devoid of the gas and dust needed for such a scenario. Every conventional door they tried was locked. Every path of inquiry led to a contradiction, a dead end. The The community was stuck staring at a set of data that felt less like an astronomical observation and more like a message with a single taunting word: impossible. But in a quiet corner of theoretical physics at a small university far from the epicenters of observational astronomy, a team of 3 researchers was about to unlock a door no one else had dared to approach. This group was led by Dr. Aris Thorne, a physicist whose career was built on exploring the beautiful, terrifying mathematics that lived in the margins of Einstein's equations. Thorne and his 2 postdoctoral researchers were not observers. They didn't command billion-dollar telescopes or process terabytes of raw data. They worked with chalkboards and code with the pure language of spacetime geometry. They were specialists in the truly exotic wormhole's naked singularities and the most maligned and forgotten object in the cosmological zoo: the white hole. For nearly a century, the white hole had been little more than a mathematical ghost, a spectre haunting the elegant equations of general relativity. If a black hole is a region of space-time from which nothing, not even light, can escape its perfect mathematical inverse, is a place from which everything must escape. A white hole is a point of violent, irreversible expulsion. It is a cosmic fountain, a singularity that only broadcasts, never receives. In classical theory, they were dismissed as physically unrealistic. To form one would require a set of initial conditions so infinitely precise they could never occur in our messy, chaotic universe. Furthermore, theorists showed that any white hole, even if it could magically appear, would be catastrophically unstable. A single photon falling towards it from the outside universe would be blue-shifted to infinite energy, instantly collapsing the white hole back into a black hole. They were seen as a mathematical artifact, a solution to an equation that nature had wisely chosen never to use. But Thorne's group had been working on a new class of models, one that linked the quantum world with the cosmological. In their view, a white hole wasn't a long-lived stable object. It was an event, a fleeting, ephemeral blast. They theorized it could be the terminal phase of a very old, very small black hole that had evaporated over trillions of years through Hawking radiation. In its final instant, rather than simply vanishing, their mathematics suggested it might rebound, undergoing a quantum bounce and explosively releasing all of its stored information and energy back into the universe in a single directed burst. It would be an echo of creation, the ghost of a dead singularity. For years, their work had been purely theoretical, a fascinating but untestable piece of cosmological speculation, published in journals read by only a handful of other theorists. It was a solution in search of a problem. Then came GRB 2319. As Thorne watched the increasingly frantic discussion of the impossible burst unfold online, he felt a chilling sense of recognition. The observational astronomers were describing piece by agonizing piece the very object his team had built on their chalkboards. He tasked his researchers Ilara Vance and Ben Carter with a monumental task to build a complete simulation of a white hole burst event using their highly speculative equations, and to compare it photon for photon with the real-world data pouring in from space. For 2 sleepless weeks, they worked fueled by coffee and the terrifying thrill that they might be standing on the precipice of a revolution. They didn't just model the burst, they modeled what an observer billions of light-years away would actually see, and their simulation produced a set of precise, falsifiable predictions for what the signature of a white hole should look like. First, it would have no progenitor. A white hole is not the death of something, it is the birth of something from a point of pure geometry. There would be no star, no binary system, nothing in the moments before the event. The space where it appeared would be utterly unnervingly empty. This matched the deep field images of GRB 231109's location, which showed nothing but the faint ancient starlight of its host galaxy. A perfect, pristine void. Second, the immediate environment would be clean. A supernova explosion throws off shells of gas for millennia before it detonates. The death of a massive star churns its stellar nursery. A white hole burst, however, would erupt into a space it had never interacted with before. There would be no surrounding nebula to absorb and re-radiate the light, no complex debris field to create confusing spectral lines. This too aligned perfectly with the unusually clean spectrum of the burst of detail that had baffled spectroscopists from the start. It was like a gunshot in a vacuum chamber. But the third prediction was their masterstroke, the key that unlocked everything. It concerned the light itself. According to Thorne's model, the initial eruption from the white hole singularity would be an object of near infinite density and temperature, a pure white-hot fireball of exotic plasma. This initial fireball would be so dense that it would be completely opaque. Photons from its core couldn't escape. What we would see first is the cooler outer layer of the expanding shell of ejector. But as this shell continued to expand and thin out over minutes and hours, our view would penetrate deeper and deeper into the receding fireball. We would be peeling back the layers of the explosion, seeing progressively hotter, more energetic regions closer to the initial event. The light wouldn't be cooling down, our line of sight would be heating up. The simulation was unequivocal. A white hole burst would produce an afterglow whose energy spectrum would not fall but climb. It would show a perfect reverse spectral evolution, shifting from lower energies to higher energies as it expanded. When Ilara Vance finally overlaid the graph from their simulation onto the real observed data from the Swift and Fermi telescopes, there was a stunned silence in the room. The curves were not just similar, they were identical. The subtle upward drift in energy, the specific rate of its spectral hardening, the exact shape of the light curve, it was all there. The model didn't just explain the anomaly, it had predicted it with terrifying precision. The impossible observation suddenly had a theoretical framework, a framework that was by all accounts completely insane. With a mix of profound excitement and academic terror, Thorne, Vance and Carter wrote their paper. They knew what they were about to do. It wasn't just publishing a new idea, it was an act of scientific heresy. They titled it cautiously, An Exotic Progenitor for GRB 20-1-9, the case for a white hole candidate. They laid out their evidence, their model, and the chilling one-to-one correspondence between their predictions and the observed data. They didn't claim it was a white hole. They simply stated that at present it was the only hypothesis in existence that fully accounted for all the bizarre features of the burst without resorting to impossible contortions of known physics. They uploaded it to the online physics preprint server on a Thursday evening. By Friday morning, the astronomical world was on fire. The reaction was immediate and it was brutal. For most of the community, the proposal was a leap too far, a violation of the principle of Occam's razor, which states that the simplest explanation is usually the right one. And a white hole, the rebound of a quantum black hole from the distant future, was anything but simple. It felt like invoking magic to explain a baffling card trick. The online forums and university colloquia buzzed with furious debate. Senior astrophysicist giants in the field penned scathing critiques. They called it an unfalsifiable fantasy, a model of last resort. They argued that there must be some unknown but still conventional physics at play, a new kind of quark star, a strange magnetic field collapse, something that didn't require tearing up the foundations of cosmology. The skepticism was not just academic, it was visceral. To accept the white hole hypothesis, even as a remote possibility, was to admit that the universe contained objects that behaved like nothing we had ever imagined. It meant accepting that causality might not be as straightforward as we believed, that information could be stored for eons inside a black hole only to be violently spat back out into a new era of cosmic history. It was a paradigm shift of the highest order, and the scientific establishment by its very nature resists such earthquakes. Yet the paper could not be dismissed out of hand. Unlike so many other speculative theories, Thorne's hypothesis wasn't just a vague idea. It was a quantitative model that matched the data. The critics could shout that it was preposterous, but they had no alternative explanation that fit the facts so well. They had their own models, but each one failed to explain that damnable, impossible, upward climbing light. And so, the battle lines were drawn. On one side, the overwhelming majority of the scientific community, armed with established physics and a healthy dose of professional skepticism, desperately searching for a more conventional answer. On the other, a tiny group of theorists and a growing number of younger, more daring observers who saw the tantalizing, terrifying beauty in the alignment of theory and data. The focus of the research had been irrevocably altered. The question was no longer simply, what are the properties of this strange burst? It had become something far more profound, a question that cut to the very heart of our understanding of reality. Is it possible that we had just witnessed for the first time in human history the other side of a black hole? The impossible light from GRB 23-1. 9 was no longer just a puzzle. It had become a choice between the comfortable, incomplete physics we thought we knew and a wild, unproven but strangely compelling vision of a cosmos far stranger than we had ever dared to dream. And so the idea was unleashed, a white hole. Not as a mathematical curiosity confined to the chalk-dusted blackboards of theoretical physics, but as a tangible, violent reality spitting fire into our telescopes. For a moment it offered a seductive kind of clarity. The impossible burst with its pristine profile and its flagrant disregard for known astrophysics suddenly had a name. It had a potential identity, a ghost from the other side of Einstein's equations. But in science, an answer that feels too simple, too perfect, is often the most dangerous thing of all. The initial wave of intellectual shock that rippled through the global community of astronomers and physicists quickly gave way to a much deeper, more troubling cascade of questions. The hypothesis, elegant as it was, had thrown down a gauntlet that challenged the very foundations of our understanding of the cosmos. Because to accept a white hole as the source of our mysterious signal, you must first answer a question that is devastating in its simplicity. Where would it come from? We understand with a beautiful and terrifying confidence how a black hole is born. You take a truly massive star, an immense nuclear furnace burning for millions of years, and you allow it to exhaust its fuel. The outward push of fusion dies, and gravity, the universe's most relentless force, finally wins the eons-long war. The star's own immense mass crushes it down past the density of atoms, past the integrity of neutrons, into an infinitesimal point of infinite density. A star dies, and a black hole is born from its corpse. There is a process, a history, a cause, and an effect, written in the language of stellar evolution. A white hole, however, has no such lineage. It is a cosmic orphan. According to the mathematics, a white hole cannot be formed by any known physical process. It cannot be the end state of a collapsing star or the result of any conceivable collision. For a white hole to exist now, it must have existed for all of time, a feature of the universe that was simply there from the very beginning. It is a solution to the equations that requires a singularity, not in our future like a black hole's, but in our distant past. Imagine watching a film of a shattered glass reassembling itself, the shards flying from the floor, defying gravity and probability, to perfectly reform the vessel from which they came. You would know instinctively that you are watching the film in reverse. That is the profound sense of unease a white hole inspires in a physicist. It is nature's film running backwards. It seems to violate the universe's most sacred and irreversible law, the arrow of time, the relentless march of entropy from order to disorder. The second law of thermodynamics is the universe's bedrock principle. Stars burn out, they don't unburn. Galaxies disperse, they don't spontaneously congregate. Yet a white hole represents a bastion of anti-entropy, a font of pure information and energy gushing out of a singularity seemingly for no reason. It is a naked, raw creation event happening in the present-day cosmos, a process we thought was reserved for the Big Bang alone. And this leads to the most chilling cosmological consequence of all. If one such object can exist, could there be others? Could our universe be seeded with these spontaneous eruptions, these cosmic wounds in the fabric of space-time, rewriting the rules of causality wherever they appear? The white hole hypothesis, in trying to solve one mystery, had cracked open a Pandora's box of theoretical impossibilities. It was a cure that seemed to many far worse than the disease. An intellectual civil war began to brew in the hushed halls of universities and the frantic email chains connecting observatories across the planet. The battle lines were drawn. On one side, a small but audacious group argued that the universe was showing us something fundamentally new, forcing us to abandon our comfortable assumptions. They contended that our failure to imagine a formation mechanism was a failure of our imagination, not a failure of nature. On the other side stood the overwhelming majority, the scientific establishment, who argued that before we resort to a solution that tears up the rulebook of physics, we must exhaust every other possibility, no matter how exotic. The burden of proof, they insisted, was not on them to disprove the white hole, but on its proponents to prove that nothing else could possibly work. And so began a desperate, brilliant, and absolutely vital search for an alternative. The hunt was on for a new culprit, a phenomenon that could mimic the impossible burst without invoking a monster from the far side of spacetime. The first port of call for the skeptics was the realm of the ultra-dense, the strange physics that governs the hearts of neutron stars. We already knew these objects were extreme. A teaspoon of neutron star material would outweigh all of humanity. They are city-sized atomic nuclei held together by a delicate balance between crushing gravity and a quantum mechanical law known as neutron degeneracy pressure. But what if under the right conditions that balance could be broken? This question gave birth to the first major alternative, a cataclysmic stellar event known as a quark nova. The theory begins with a rapidly spinning neutron star, a magnetar perhaps already pushed to the very brink of stability. An external trigger, a nearby supernova shockwave, a significant accretion of matter from a companion star, or even an internal starquake, could provide the final nudge. That last tiny bit of pressure could be enough to overwhelm the forces holding the neutrons apart. And in that instant, the neutrons themselves would collapse. They would dissolve into their constituent components, the fundamental particles known as up and down quarks. This isn't merely a change in pressure. It is a phase transition as fundamental as liquid water freezing into solid ice, but infinitely more violent. The entire star, in a fraction of a millisecond, would transform from a sea of neutrons into a sea of free quarks, a new state of matter called a strange quark star. During this transition, a colossal amount of binding energy would be released in a focused, terrifyingly powerful burst. The proponents of this model argued that it had several advantages. It relied not on rewriting the laws of general relativity, but on pushing our understanding of the strong nuclear force, the force that binds atomic nuclei into uncharted territory. This was frontier physics, certainly, but it was not supernatural physics. The quark nova could in principle produce an immense amount of energy from a very small compact source, potentially explaining the burst's intensity and apparent point-like origin. Simulations were run on supercomputers' complex models that attempted to capture the physics of this stellar metamorphosis. They painted a picture of a shockwave erupting from the star's core, an explosion of gamma rays and neutrinos that could perhaps resemble what our telescopes had seen. But the quark nova model was not without its own serious problems. As the simulations grew more sophisticated, they revealed a messier reality. Such a phase transition would likely be turbulent and chaotic, not the clean, almost mathematically pure pulse of energy that had been observed. The models predicted a complex afterglow, a lingering cloud of debris and radiation, as the newly formed quark star settled down. Yet when we looked back at the location of our impossible burst, we saw nothing. No nebula, no fading remnant, just the unnerving quiet of empty space. Furthermore, the light signature, the specific frequencies of energy released, didn't perfectly match what the quark nova models predicted. The theory could produce the right amount of energy, the right brute force, but it struggled to replicate the event's pristine, almost delicate fingerprint. It was like finding a victim of a gunshot, but the only suspect you have is a cannon. The power is there, but the signature is all wrong. The quark nova was a powerful contender, a testament to the ingenuity of astrophysicists, but it wasn't a perfect fit. The mystery remained, and the search for other explanations intensified, pushing researchers to consider even more bizarre scenarios. If a single object transforming wasn't the answer, perhaps two objects colliding was. We are living in the golden age of gravitational wave astronomy, where we can now listen to the cosmic symphony of merging black holes and neutron stars. We have seen what happens when two neutron stars collide. The result is a killer nova, a magnificent but relatively short-lived explosion that forges heavy elements like gold and platinum and scatters them across the cosmos. It is a powerful but well-understood event. But what if the objects that collided weren't standard neutron stars? What if they were the hypothetical endpoints of the quark nova itself? What would happen, theorists asked, if two quark stars or even a quark star and a black hole were locked in a death spiral? The physics involved is almost incomprehensibly complex. It would be a collision of matter already at the most extreme density the universe allows. The resulting explosion would make a kilonova look like a firecracker. The model suggested that the direct conversion of the quark matter into pure energy could release a burst so clean, so efficient, that it might bypass the messy debris problem that plagued the single quark nova theory. It could potentially create a single, unadulterated flash of light and energy that would leave almost no trace behind. This idea, the collision of ultra-compact exotica, was tantalizing. It used the established framework of binary mergers, but swapped out the known actors for more mysterious ones. Yet this theory too rested on a pyramid of assumptions. Firstly, it requires quark stars to exist in the first place, something for which we have no direct evidence. Secondly, it requires them to exist in stable binary systems. And thirdly, it requires us to have been fantastically impossibly lucky. The predicted rate of such mergers is astronomically low. While standard neutron star mergers might happen once every 10,000 years in a galaxy like ours, the merger of two quark stars might happen less than once in a billion years. To propose that this is what we saw is to propose that our telescopes were pointed at the right place at the right time to witness an event so rare it might be unique in the observable universe's history. While not impossible, it's a solution that relies on a statistical miracle, something that makes many scientists deeply uncomfortable. Science prefers explanations that are common, not ones that require us to have won the cosmic lottery. The beautiful, clean signal we had received felt less like the chaotic shrapnel of a collision, and more like something else, something more fundamental. This led the search to its third and perhaps most haunting alternative, an idea that reached back not just through stellar history but to the very dawn of time itself. It drew upon a theoretical concept proposed by Stephen Hawking decades ago: primordial black holes. These are not the black holes formed from collapsing stars. These, if they exist, are microscopic fossils from the Big Bang, forged in the first chaotic moments of the universe, when pockets of energy and matter were so dense they could spontaneously collapse under their own gravity. For billions of years, these tiny black holes would have drifted silently through the cosmos, completely invisible, their gravitational influence too small to be noticed. But black holes, as Hawking brilliantly demonstrated, are not eternal prisons. They evaporate. Through a quantum mechanical process now known as Hawking radiation, they leak particles back into the universe over immense, almost unimaginable timescales. For most black holes, this process is so slow as to be irrelevant. But for the smallest primordial black holes, those born with the mass of a mountain compressed into the size of a proton, their lifetime could be finite. Their 14 billion year journey across the cosmos would be coming to an end right about now. The final moments of a black hole's evaporation would not be a gentle fizzle. As it shrinks, its temperature skyrockets and the rate of radiation increases exponentially. In its last second of life, it would unleash all of its remaining mass energy in a single definitive flash of high-energy gamma rays and exotic particles. It would be a final violent scream, a ghost of the Big Bang finally giving up its 14 billion-year-old secret. This explanation had a profound, almost poetic elegance. It connected our mysterious burst directly to the birth of the universe. It could explain the point-like source and the immense energy. And it could explain the lack of any stellar remnant or nebula, because there was never a star to begin with. The black hole would have simply vanished, leaving behind nothing but the expanding shell of its final breath. It was a beautiful, compelling story, but once again the devil was in the details. The standard model of Hawking radiation predicts a very specific energy signature for this final burst, a chaotic spray of all types of particles. The impossible burst, however, was not chaotic. It was strangely coherent, almost pure. To make this theory work, you would have to rewrite the laws of Hawking radiation, proposing new undiscovered physics that could make the final evaporation far more focused and orderly than previously thought. And so here we stand at a great intellectual crossroads. The scientific community is fractured, armed with a portfolio of extraordinary theories, each vying to explain the inexplicable. We have the white hole, a solution of breathtaking simplicity that seems to require a miracle of cosmic creation and threatens to upend our understanding of time itself. We have the quark nova, a hyper-energetic phase transition grounded in nuclear physics, but which struggles to explain the pristine nature of the signal. We have the collision of exotic quark stars, a plausible mechanism for immense energy release, that relies on a chain of unproven assumptions and a dose of incredible luck. And finally, we have the ghost of a primordial black hole, a dying echo from the dawn of time, an elegant theory that requires us to invent new quantum gravity physics to make the final details fit. Each path forward is fraught with uncertainty. Each explanation solves one part of the puzzle only to create a new one. The debate is no longer just about a strange flash of light in the sky. It has become a battle over the fundamental nature of reality, a fierce contest between the known laws of physics, pushed to their absolute limit, and the terrifying possibility that we have stumbled upon something that operates by new laws altogether. The theoretical stalemate is absolute. To move forward, to choose a path, we need more than elegant equations and clever simulations. We need a new piece of evidence, a Rosetta Stone from the source of the burst itself that can break the deadlock. We need a clue that can turn one of these wild speculations into a scientific fact. The silence that followed the initial storm of discovery was in its own way just as profound. For 7 years, the astronomical community had been locked in a state of civil yet fiercely passionate intellectual warfare over the impossible burst. The event catalogued as GRB Omega had become a celestial Rorschach test. Look at its light curve and you might see the death of a bizarre metal-free star from the dawn of time. Analyze its polarization, and you could argue for a magnetic cataclysm beyond anything our models could produce. And if you possess the courage to challenge the very foundations of physics, you saw what you desperately wanted to believe, or desperately feared, was true a rupture in reality itself. The white hole hypothesis, once a fringe idea whispered in university corridors, now had its champions, its critics, and its own growing mythology. But mythology is not science. Without new evidence, all we had were elegant theories wrestling in the dark, each claiming victory with no referee to make the call. The debate had reached a stalemate, a gravitational deadlock as intractable as any binary star system. The universe, however, was not finished speaking. We had simply been using the wrong ears to listen. Far from the shimmering mirrors of telescopes that drink in ancient light, humanity had been building new senses. Deep beneath the Antarctic ice, a crystalline lattice of detectors waited patiently for the universe's most elusive messengers. These were the neutrino observatories designed not to see but to feel the faintest tremors of cosmic events, as ghostly particles born in the hearts of stellar furnaces and cosmic collisions passed through the entire planet as if it were empty space. And on the Earth's surface in the United States, Europe and Japan, a new generation of gravitational wave observatories had come online. Their lasers, stretched across kilometers of vacuum-sealed tubes, were now so exquisitely sensitive they could detect a distortion in spacetime 1,000th the width of a proton. They were built to hear the cymbal crash of merging black holes, the drumbeat of colliding neutron stars. No one expected them to hear a whisper from the past. No one expected them to find an echo of GRB Omega 7 years after it had vanished from our skies. The signal, when it finally arrived, was not a clamour, but a spectre. It didn't come from the sky, but from the ground, pulled from the background noise of Earth's own groaning crust and the ceaseless quantum fizz of empty space. The global gravitational wave network registered something so faint, so utterly alien, that the initial detection algorithms flagged it as an error. Black hole mergers have a signature sound, a cosmic chirp, that rises in frequency as the two behemoths spiral towards their doom. This was the opposite. It was an anti-chirp, a note of rising complexity that fell into a perfect simple tone. It was the sound of a bell unringing. It was the space-time signature of an object not violently collapsing inward, but expanding outward, its complexity blooming into a state of serene simplicity. It was a waveform that, according to every known model of gravitational physics, should not exist. A sound from a throat that should be unable to sing. Panic, confusion, and then a jolt of pure adrenaline shot through the astrophysics community. The signal was weak, buried in noise, but its direction on the sky was unmistakable. It pointed directly to the vacant patch of cosmos where 7 years earlier, GRB Omega had detonated. The implication was staggering. A gravitational wave echo travelling at the speed of light should have arrived with the original burst of light not 7 years later. For it to arrive now meant it must have taken a different path, a longer path, a path that had been warped and delayed by some colossal gravitational lens between its source and us. This was the key. The team scrambled, tasking every available telescope to map the intervening space, looking for the massive galaxy cluster that must be responsible for such a delay. But there was nothing there. The void between us and the source was for cosmological purposes empty. The signal had not been delayed by a lens. This was something else. A second act from an object that was supposed to be gone forever. Just as this new paradox began to solidify, a message came from the South Pole. The neutrino physicists had found something. Sifting through petabytes of archived data from the exact week of Omega's original eruption, they isolated a single impossibly high-energy neutrino. One solitary particle, a trillion electron-volt ghost, had streaked through their ice-bound detector. Its trajectory was a perfect match for GRB Omega. A single data point is not a discovery. It is an anomaly, a statistical fluke. But then they checked the precise time of arrival, and the world tilted on its axis. The neutrino had arrived a full 82 seconds before. The first gamma-ray photons from the burst were detected by our orbiting telescopes. This is a violation of the most fundamental tenet of cosmic observation. Nothing, not even a whisper of information, should escape an explosive event before the explosion itself begins. An effect cannot precede its cause. It was like hearing a clap of thunder before the lightning bolt that produced it had even formed. Here then was the impossible puzzle laid bare. An initial burst of light with a chemical signature from a universe that hadn't existed yet. 7 years later, a gravitational wave signal of an object expanding, not collapsing. And buried in the archives, a ghostly particle messenger that arrived before the message was even sent. These three pieces of evidence were not just contradictory, they were mutually exclusive. They painted a picture of an object that was simultaneously ancient and new, an explosion that was also an expansion, an event that sent out an echo of its own arrival. It was a cosmic beast that defied all classification, a chimera stitched together from the violation of known laws. The community was no longer just deadlocked, it was lost in a fog of profound and terrifying ignorance. We had spent decades building a grand cathedral of cosmic understanding, and now it felt as if we had discovered that its entire foundation was resting on sand. The moment of greatest confusion, however, is often the moment that precedes the dawn of absolute clarity. The breakthrough did not come from a telescope or a detector, but from the quiet hum of a supercomputer cluster in Munich. There, a team of theoretical physicists led by the visionary Dr. Aris Thorne had abandoned the conventional approach. Thorne argued that everyone was trying to fit the pieces to an existing puzzle, trying to explain the anomalies away within the framework of general relativity. What if he proposed in a now legendary seminar the framework itself is incomplete? What if these are not three separate impossibilities, but three perfectly logical consequences of a single new piece of physics? Thorne's team wasn't modelling stars or black holes. They were modelling spacetime itself at the quantum level, a fiendishly complex realm, where gravity and quantum mechanics, the two pillars of modern physics, meet and break down. They were exploring ideas from loop quantum gravity, a theory that suggests spacetime isn't a smooth sheet but a fabric woven from indivisible quantum loops. In this theory, there are no true singularities. A black hole cannot collapse to an infinitely dense point. Instead, as a dying star collapses, it reaches a point of maximum possible density, a state known as a Planck star. At this mind-boggling density, quantum pressure, the universe's ultimate stop sign, kicks in. Spacetime itself resists. It refuses to be crushed into non-existence. And so it does something that sounds like science fiction. It bounces. The inward collapse reverses in a violent quantum mechanical rebound, turning the object inside out. A collapsing black hole in this view doesn't just end, it transitions. It becomes its temporal opposite. It becomes a white hole. This wasn't just a theory, it was a cascade of predictions. A quantum bounce would not be instantaneous. The immense gravity of the collapsing object would warp time so severely that for an outside observer, this bounce, which might take a fraction of a second inside the event horizon, would appear to take billions of years. A black hole forming in the early universe could, from our perspective, be bouncing today. Thorne's team began to run the numbers feeding the strange properties of GRB Omega into their new simulation. The first result appeared on the screen, and the room fell silent. The simulation showed that as the quantum bounce occurred, a shockwave would ripple through the newly ejected matter. This shockwave would create a thermal environment identical to the Big Bang itself, a brief localized pocket of creation. Matter forged in this furnace would be blasted outward, and it would look to our telescopes exactly like pristine primordial material from the dawn of time, completely free of the heavy elements that contaminate our modern universe. It perfectly explained the impossible chemical signature of the light. They had solved the first paradox. Then they modelled the particles. The simulation revealed that as the bounce began before the main explosive eruption, ultra-high energy neutrinos could be created. These particles, interacting so weakly with gravity and matter, could tunnel through the still-forming event horizon moments before it fully inverted. They could escape into the cosmos just ahead of the main burst of light. The simulation predicted their arrival time down to the second. A neutrino messenger arriving 82 seconds early was not a violation of causality. It was the signature of a quantum bounce. The second paradox fell. The final piece was the gravitational wave signal. This was the masterstroke. A black hole merger creates a ring down, a final shudder of space-time as the newly formed event horizon settles into a perfect sphere. Thorne's model predicted that a quantum bounce would do the same, but in reverse. The newly formed, rapidly expanding white hole event horizon would also shudder as it burst into existence, emitting gravitational waves. It would be a ring up, a space-time vibration that grew into stability. But why did it arrive 7 years late? Thorne's simulation provided the chilling, beautiful answer. The interior of a black hole where the bounce occurs is a region of such extreme gravitational time dilation that it essentially disconnects from our flow of time. The gravitational waves from the bounce do not travel through space-time in the conventional sense. They travel along the edge of this temporal schism. Their path to us is fundamentally different, longer and more contorted than the path taken by the light and neutrinos that escape later. The model predicted a delay, a cosmic echo whose exact timing depended on the mass of the original object. They plugged in the mass estimated from GRB Omega's brightness. The computer churned for a moment and then returned a value for the gravitational wave delay. 6.91 years. It was a perfect match. A wave of understanding of consensus swept across the globe. It was a moment of scientific rapture. The impossible burst, the early neutrino, the delayed anti-chirp. They were not contradictions. They were the three pillars of a new reality, the distinct resonant notes of a single cosmic chord. We were not looking at a primordial white hole that had somehow survived since the beginning of time. We were looking at something far more profound. We had witnessed the end of a black hole's life. We had seen for the first time a black hole die not by slowly evaporating over trillions of years, but by transforming by undergoing a quantum resurrection into its cosmic opposite. The central mystery of GRB Omega was solved. It was the birth announcement of a white hole emerging from the quantum ashes of a black hole that had formed billions of years ago. It was a space-time reversal event. The implications were almost too vast to hold in the mind. The information paradox, the question of what happens to the information that falls into a black hole, was suddenly answered. It isn't destroyed. It's stored, compressed to a quantum state, and eventually ejected back into the universe. The life cycle of the cosmos was no longer a one-way street to oblivion. It was a cycle of collapse and rebirth. We had found a crack in the facade of cosmic finality, a hint that even from the most absolute of endings, a new beginning is possible. We had sought a monster and found a mechanism of cosmic recycling. The universe, it turns out, is not a graveyard for lost information. It is an archive. And we had just witnessed the opening of its most ancient and secret vault. The story of GRB Omega was over, but a much larger story, the story of a universe that can heal its own wounds and reverse its most extreme collapses, was just beginning. We had lifted a veil expecting to see the face of destruction, and had found staring back at us the engine of creation itself, undefined. And so, the light, after its impossible journey across billions of years, finally gave up its secret. The ghost that had haunted our telescopes, the signal that defied our models, was not in the strictest sense the mythical white hole we had dared to imagine. It was something perhaps even more profound, a phenomenon born from the violent collision of physics we once thought irreconcilable. A quantum gravitational rebound, a momentary breathtaking glimpse into the engine room of space-time itself, or a collapsing star on the very precipice of becoming a singularity recoiled. It shuddered not with an explosion of matter, but with a shockwave of pure information echoing forward from a future that should not yet exist. It was a wrinkle in causality, a stutter in the cosmic clock, an event so rare it might happen only once in a galactic lifetime. To put a name to it, to categorize it as a quasi-white hole event or a Planck star emergence, feels almost like a disservice, a clinical label for a miracle. Because the true legacy of this celestial phantom was never going to be about confirming a decades-old theory. Its true value, its enduring power, lies not in the final answer we painstakingly uncovered, but in the spectacular, transformative, and deeply human journey it launched us on. We were sent chasing a myth, and in that chase we stumbled upon a deeper truth. It forced us to become cosmic detectives on the grandest possible scale, piecing together clues written in the language of gamma rays, polarized light, and the subtle warping of gravity itself. Every dead end we encountered, every discarded hypothesis was not a failure. It was a necessary step in climbing a mountain whose peak we couldn't even see when we began. Think back to that initial moment of discovery, a moment you witnessed with us. An impossible burst of energy from a void where nothing should be. It was an anomaly, a single defiant pixel on a cosmic map that should have been dark. It could have been dismissed as an instrument error, a statistical fluke destined for an obscure footnote in an academic journal. But it wasn't, because a handful of scientists, fueled by a relentless curiosity that is the very lifeblood of our species, refused to let it go. They saw past the improbable data to the extraordinary possibility it represented. They asked the one question that ignites all discovery: what if? That question echoed through observatories and supercomputer centers across the globe, uniting teams that had once been rivals, forging a collaboration as vast and intricate as the mystery itself. We sifted through petabytes of data, a digital torrent from dozens of telescopes, each capturing a different facet of the event's fleeting existence. We watched as simulations running for months on end crashed against the stubborn reality of the signal, our best understanding of physics, failing time and again to replicate what nature had so effortlessly produced. You saw the debates, the passionate arguments in conference halls and late-night video calls as brilliant minds wrestled with the implications. Was it a new type of supernova, a collision of exotic stars made of strange matter, or the fantastical, the impossible, the fabled opposite of a black hole? The search became a testament to our persistence, a refusal to accept that the universe could be anything less than astonishing. We were like ancient mariners charting a new world, sketching coastlines in the dark, guided by a single inexplicable star. The pursuit demanded more than just intellect. It demanded imagination. We had to unlearn what we thought we knew to loosen our grip on the comforting pillars of established theory. General relativity, our masterful description of the grand cosmic dance of gravity, had shown us the abyss of the black hole. Quantum mechanics, our profoundly successful theory of the infinitesimally small, whispered that no information could ever truly be lost. For decades, these two great triumphs of human thought had stood apart, reigning over their separate domains. The impossible burst occurred precisely in the chasm between them. It was a bridge violent and ephemeral across that conceptual divide. It was a message from the quantum foam, the very fabric of reality at its most fundamental level, screaming that our neat separation of cosmic law was a fiction, a convenient approximation for a universe far more unified and far more bizarre. The resolution that this was the signature of space-time itself, healing from a near singularity, has shattered our understanding of stellar death. We once viewed the collapse of a massive star as a one-way street, a terminal plunge into the infinite density and darkness of a black hole. Now we are confronted with a new astonishing possibility, that the process is not always final, that at the Planck scale, where gravity becomes a quantum force, the collapse can be arrested and violently reversed, not in an explosion of matter, but in an outward cascade of pure temporal energy. It suggests that the universe has a fail-safe way of avoiding the paradox of the singularity, of smoothing over the infinities that have long plagued our equations. This isn't just a new type of celestial object. It is a new chapter in the cosmic rulebook, a fundamental principle of gravitational physics we never knew existed. This single event has become a cosmic Rosetta Stone. Before its discovery, theories about quantum gravity were elegant mathematical constructs, confined to whiteboards and theoretical papers. They were ideas awaiting a test, prophecies without proof. The burst provided that proof. It gave us our first tangible observational data from the edge of a singularity. Suddenly, abstract concepts like loop quantum gravity string theory and causal set theory were no longer just academic exercises. They were competing suspects in a cosmic crime scene, and we could finally test their predictions against real-world evidence. The polarization of the initial gamma rays, the subtle gravitational lensing in the aftermath, the unique temporal signature of the burst's decay, these were the fingerprints left behind, allowing us to rule out some theories and lend powerful new credence to others. We are now living in a new era of physics, one in which we can empirically study the birth of space-time, not just theorize about it. The implications ripple outward, touching every corner of cosmology. The information paradox, the profound puzzle of what happens to the information that falls into a black hole, may now have a potential solution. If a collapsing star can rebound and release a shockwave of its history encoded in quantum gravitational waves, then perhaps information isn't destroyed at all. Perhaps it's simply rebooted, re-injected back into the universe in a form we're only now learning to detect. This idea, once relegated to the fringes, is now at the forefront of theoretical physics, all because of a flicker of light from an empty patch of sky. It forces us to reconsider the nature of time itself, suggesting that causality might be more flexible than we ever conceived, allowing for echoes from the future to influence the past at the universe's most extreme tipping points. Even our understanding of the universe's ultimate fate is now being re-evaluated. If matter isn't necessarily lost forever in singularities, what does that mean for the long, slow decay of the cosmos? Could these quantum rebounds be a source of cosmic re-energizing? A mechanism that prevents the universe from descending into a final permanent heat death? These are no longer questions of pure speculation. They are active fields of research with dedicated teams designing new observational strategies, all stemming from the aftershocks of that one impossible signal. It was the cosmic equivalent of discovering a new fundamental force of nature, a revelation that redraws the map of reality and points toward continents of knowledge we never knew were there to be explored. And so, we find ourselves looking to the future, not with a sense of completion, but with a renewed sense of infinite possibility. The journey hasn't ended, it has just begun, and the questions are now grander, deeper, and more exciting than ever before. If one such event could occur, how many more have we missed? Are these rebounds happening silently all around us, their signatures too faint for our current instruments to catch? Answering these questions requires a new generation of eyes on the universe, and the plans are already underway. We are entering an age of unprecedented observational power. Imagine vast arrays of gravitational wave detectors not on Earth, but in space, forming a celestial web so sensitive it can feel the tremor of a single collapsing star halfway across the cosmos. Imagine a new fleet of high-energy telescopes capable of measuring the polarization of every single photon from a distant burst, providing us with a holographic view of the event's geometry. These future observatories, like the Laser Interferometer Space Antenna and the proposed Einstein telescope, are being designed with this mystery in mind. Their prime directives are no longer just to find black holes or neutron stars, but to hunt for their echoes, to listen for the whispers of quantum gravity in the silent darkness between galaxies. We will build spectrographs that can dissect the light from these events with surgical precision, searching for the telltale chemical fingerprints of matter being born directly from the energy of space-time. We will deploy neutrino detectors deep within the Antarctic ice, hoping to catch the ghost particles that might be the first heralds of a star's quantum recoil. This is the tangible legacy of the impossible burst it has reshaped, the very architecture of our scientific ambitions, pointing our most powerful tools toward a horizon we previously didn't even know how to look for. We are in a very real sense learning a new cosmic language. For centuries we have studied the universe through the light of stars and the pull of gravity as described by Newton and Einstein. But the impossible burst was written in a different script, the syntax of quantum gravity. Deciphering it will be the great work of the 21st century. It will require a new generation of physicists, astronomers and mathematicians' young minds, inspired by this very story, who will grow up in a world where the line between a black hole and a white hole has been blurred forever. They will inherit not a complete picture of the universe, but a thrillingly incomplete one with a giant tantalizing question mark placed right at the heart of creation. In the end, did it matter that the object wasn't a classic white hole, a perfect cinematic reversal of a black hole? Absolutely not. What we found was infinitely more valuable. A white hole would have been an answer that confirmed a theory. What we discovered instead was a question that shattered a dozen theories. It was a cosmic anomaly that held up a mirror to our own understanding and showed us the gaps, the limitations, the exhilarating scope of our own ignorance. It reminded us that the universe is under no obligation to conform to our expectations to fit neatly into the boxes we construct for it. Its genius lies in its capacity to perpetually surprise us, to present us with phenomena so strange, so counterintuitive. They force us to grow, to think bigger, and to reach further. This is the enduring promise of science, not to find all the answers, but to revel in the pursuit of ever deeper questions. The impossible burst was a gift. It was a fleeting glimpse into the machinery of reality, a reminder that we live inside a grand, unfolding mystery. It has permanently altered our perspective, colouring our view of every star in the sky. When you look up at the night sky now, you are not just seeing a collection of placid, burning suns. You're looking at a field of potential impossibilities, a realm where stars can die and be reborn in a flash of quantum light, where time can bend back upon itself, and where the laws of physics are still being written. We have been invited by a silent flash light years away to participate in the writing of those laws. The universe whispered one of its deepest secrets, and the most wonderful thing of all is that we were here listening, ready to begin the next stage of our unending journey into the light.